Hello everyone and welcome to our new video predicting stock prices using recurrent neural networks. Have you ever wondered how AI can predict stock prices? One of the key tools in deep learning for time series prediction is the recurrent neural network, or RNN. In this video, we'll break down what RNNs are, how they work, and why they're used in stock market predictions. Make sure to stick around until the end because I'll be showing you the actual results of our model in action. Let's dive in. Before we go any further, I want to let you know that I've decided to split this video into 3 parts to keep things digestible and beginner friendly. In part 1, we'll explore what recurrent neural networks are, and to make sure we're all on the same page, I'll also include a quick dive into how basic neural networks work. So if you're new to this, don't worry, I've got you covered. During part 2, we're going to do a concise walkthrough of how to implement a recurrent neural network for stocks trading. And finally, in part 3, I'm going to go over the results of the model, show you what worked, what didn't, and offer my insights into what happened. Let's start from the beginning. What is a feedforward neural network? Well, it's the most basic type of neural network, and it's a great place to begin if you've never seen one. Here's a network with 3 inputs, 4 hidden neurons, and 2 outputs. Information flows in one direction from input to output, and there's no loops or no memory, hence the name feedforward. To go from one layer to the next, for example from the input layer to the hidden layer, we multiply our input vector by a matrix of weights, often called W, and then we add a bias vector, which just shifts things slightly. Mathematically, this looks like this, but we are not done yet. After this linear transformation, we apply something called an activation function. In this case, we'll use ReLU, which is short for rectified linear unit. And the function is quite simple. Anything below 0 becomes 0, and everything above stays the same. So why do we do this? Well, without it, all layers would just collapse into one big linear transformation, and neural networks would lose their ability to learn complex nonlinear patterns. ReLU basically breaks that linearity and helps our network model much more complicated functions, like the chaotic nature of stock prices. After the activation, we repeat the same process to go from the hidden layer to the output layer, by choosing another weight matrix, another bias, and maybe another activation. Now that we've seen how information flows through our network, from input to hidden layer and then to output, let's talk briefly about how this model learns. To keep things simple, let's ignore biases for now. What we're left with is 2 weight matrices, one to go from the input to the hidden layer, and another one to go from the hidden layer to the output. These weights are what the neural network is really trying to figure out. During training, our algorithm adjusts its numbers over and over again to improve its predictions based on the input data. This process is called backpropagation, but we won't get into the math of it in this video. If you're curious, let me know in the comments and I can make a video explaining exactly how it works. For now, just know this. The neural network learns the ideal values for these weights so that, given our input, like stock data, it can make the most accurate prediction possible. Now, let's talk about recurrent neural networks, or RNNs, which are designed to handle sequential data like stock prices. Our input at each time step is the vector x of t, while the subscript t just means it's data at time step t. This could indicate features like the stock's open, high, low, close, and volume for that day. Here's how it works. The RNN has a hidden state, let's call it h of t, which stores information from the past. The current input, x of t, and the previous hidden state, h of t minus 1, are both used to compute h of t, which in turn is used to generate the output y of t. Whenever you see these arrows, think of matrix multiplications. X of t and h of t minus 1 are each multiplied by weight matrices, and the results are combined to compute the new hidden state. Formally, we compute the hidden state like this. Now, you may have noticed that this time I'm not using ReLU as the activation function. Instead, I'm using something called the hyperbolic tangent, or tang. I've decided to include a quick overview of tang in this video because of how important it is in deep learning, especially for sequential data like time series. The tang function is a smooth S-shaped curve that takes an input and squashes it between -1 and 1. Mathematically, it is defined as this. It's centered around 0, which helps keep the network's activation balance between positive and negative, making it easier to model changes over time. That's why tanh is widely used in tasks like stock market forecasting, natural language processing, and other sequential data problems, areas where capturing the direction and magnitude of change is crucial. Of course, rel and sigmoid are also extremely important activation functions in neural networks. Here you have a comparison of the three. Let's return to our recurrent neural network. You'll remember that the arrows represent multiplying by a matrix of weights and then adding a bias. At this stage, we compute the output by taking the hidden state vector and multiplying it by another matrix of weights, then adding the bias again. So in this vanilla recurrent neural network, we're estimating 3 weight matrices. One for the input to hidden state, one for the hidden state to itself, and one for the hidden state to output. To understand how recurrent neural networks work across time, we can unfold the network, so let's shift our graph upward and make space to visualize this. We will initialize our hidden state, typically just with zeros, and then at time step 1 we will fit in our first input x of 1, and the network uses it to generate the first hidden state h of 1, which then produces the first output y of 1. At time step 2, we fit in the next input x of 2, but this time we'll also use the previous hidden state h of 1 to calculate the new hidden state h of 2, which then gives us y of 2. And the same process repeats at time step 3, time step 4, and so on. This structure gives RNNs their power. They can use memory of previous steps to inform future predictions, which is exactly what we want when analyzing sequences like stock prices. Now let's look at a practical example. In this animation, the recurrent neural network unfolds over several time steps, but this time we're doing something slightly different. Instead of producing an output at every step, the network will only generate an output after the 7th observation. That's because we're trying to predict the future price of a stock using information from the past 6 days. So what's happening here is that we feed the model a sequence of inputs, one for each of the last 6 days, and only after the full context is processed does the model produce a single prediction at the time step 7. This approach is common in time series forecasting, where we care less about intermediate output and more about a final informed estimate. And remember, we're assuming the model has already been trained with backpropagation, so it has learned how to make this prediction based on patterns it's seen in past data. Alright, moving on to part 2. Now that we understand how recurrent neural networks work, it's time to dive into a step-by-step implementation for real trading using these models. In this practical example, I've pre-selected some data from the Tesla stock. At each time step, which in our case is going to be 1 trading day, we're going to capture several key features. Those are the closing price, trading volume, daily high, low, and a few other technical indicators. These become our input vectors, and in this animation you'll see the model make a prediction based on the past 4 days. But just so you know, the recurrent neural network I train actually uses the past 50 observations. Now that we've seen how to train a recurrent neural network, let's move on to the results and break down what worked and what didn't. The model has been trained, and here I'm testing it on 300 days of unseen stock data. This is crucial to assess generalization and check for overfitting, where a model memorizes the training data but fails to make good predictions on new data. That's exactly why we keep this separate test set. This is how the model performs after just 10 epochs of training. As you can see, the predictions are quite rough and the model hasn't yet learned meaningful patterns. It's essentially guessing, and there's no clear alignment between its output and the actual price movements. Now let's look at the same model after 1000 epochs of training. The predictions are noticeably more stable and follow the general direction of the stock more closely. We're saying that the model is starting to learn temporal dependencies in the data and extract trends. Zooming into this section here, you'll notice something more interesting. The model seems to be behaving a little bit like a momentum strategy. That is, if the stock is going up, it tends to predict continued upward movement, and when the stock goes down, it expects the trend to continue. This kind of pattern following isn't uncommon, especially in financial time series, but it also means the model may struggle when a trend suddenly reverses. So while this shows promise, it also highlights that RNNs, like any other model, carry assumptions, In this case, the recent trends are predictive of what comes next. I hope you enjoyed the video, as I definitely enjoyed making it. If you're interested in other ways to predict stocks using machine learning, make sure to check out my video on the K-unbounded algorithm, where I explore a completely different strategy based on reinforcement learning. And if you'd like to support the channel, I've linked my Patreon below. I'll be uploading the code I used to create this RNN model, and I'll also be adding some extra tutorials on how to use it effectively. I'm aiming to have those up before the end of May, so stay tuned. Thanks again for watching, and I'll see you on the next one.